Hello everyone and welcome to this video which is going to be about ftrace. Now this is the first video in the series of tracing where I actually get into the details of how we can use these tracing tools in the Linux kernel. Now ftrace is one of the oldest um, tools there in the Linux kernel which is actually built into the kernel image. So it's not like a tool that you would install it, but it's a tool that you would have to have enabled by providing the right kernel configurations. And now most of the kernels that I've ever seen, they have ftrace enabled by default, but if it's not there, then you probably have some of the kernel configuration options missing. So I'm gonna actually switch myself to root by using sudo su switch user, and then I'm gonna, you know, switch to root. So I'm now in root, and like if I say who am I, it's going to be root. Okay. The API for ftrace is implemented as part of the file system. So it's kind of like a what they call in Linux a pseudo file system, which is not really backed by any files on the disk, but rather it's an API that exposes a bunch of variables and functions and whatnot in the form of a file. So when you read and write to those files, there are certain actions um, taken up by kernel in response to the reads and writes. Okay, sys kernel debug, and make sure you put the debug there. So if you go inside sys kernel debug, you'll see a bunch of stuff here. Now, all of these are interesting, actually, capabilities and features such as the scheduler and whatnot. But today, what I'm going to talk about is ftrace, which is going to be here in tracing. So cd tracing. Now, sometimes I prefer to kind of create like an alias or like a environment variable that would point to this place and then you know uh, work with this from my actual user, not through the root, like by doing sudo typing sudo, but it's just more convenient this way, at least for the purpose of this video, because I'm going to be typing a lot of these commands and I don't want to say sudo all the time. Okay, so here we have a bunch of files. Now, first off, let me tell you what this ftrace going to give you. Let me give you a sample output of ftrace. Now, this is a sample output of ftrace. This is actually a function trace. It's going to tell you what function was called. Or you could configure it such that you get function graphs, right? This function calls this function, that function, and so on and so forth. Or you could configure it such that you get the events, right? These are events that are triggered in the system. These are events, like these are trace points, if you may, right? As opposed to function calls. Trace points are as I explained in the previous video, are an API that you call inside the kernel code, or in fact user code for that matter, and that hitting that point would result in an event like this being generated and saved to some buffer, which you can then inspect. Okay, so that's how the output is going to look like. But these set of files is how we configure ftrace and how we actually read the trace off of it. There are several kinds of tracers. Now there's a file here by the name of available tracers. So if I cat available tracers, you can see that I have a hardware latency block, device related memory map IO trace function graph, which is going to give you this guy, function graph tracer. And we have these are for basically tracing the scheduler performance. And then we have the function, which is just going to tell you what this function was called, that function. It's not going to give you a function graph. Like, it's basically going to give you something like, where was it? This one, this function, that function, you see. So it's just going to tell you this function is called and so on and so forth. And also, at last, we have the NOP tracer, which is the basic event tracer, which is going to give you output such as this. These are the events, right? So these are not, sorry, these are not functions. These are events. These are trace points that you can enable, disable on the fly. Okay, so these are the different kinds of tracers. Now, we're not going to cover all of these. There's a very good documentation here about how this whole thing works and an ftrace, and I'm going to basically kind of browse through this and pick some points and kind of walk you through them and to see how it's used. And I, to be honest, myself, from time to time, have to go back to this page and try to, find some obscure function that I don't tend to use that often. So it's completely okay. And I, in fact, encourage you to go here and use it, or after some time you kind of develop your own cheat sheet for yourself that you uh, put in the common things that you might do in a cheat sheet, or and you might want to get it from there. Okay, so that's the kind of tracers that I have, and this is so the current tracer here tells me what tracer am I using right now. So if I say cat this tracer, I'm going to be using the knob tracer, meaning that if I do any trace, I'm going to get something like that, right? Okay, so that's that. Now, where are these events, by the way? So, okay, good, very good. I want to go and trace some events. What am I going to do? Well, here there's a folder. It's called events. So if you go into that folder and you see these are all the events that the Linux kernel has. And by the way, ftrace, I forgot to mention this in the beginning, ftrace is a kernel tracer. So it only traces kernel space code. You really like, at least I've never used it for user space tracing, and I don't think it works that way. Um, so anything in the kernel space you want to trace, ftrace is actually a good option for that. Okay, so these are the events. And basically, every folder contains a group of events. So these, for instance, are for the general purpose IO group. Let's see. So the block is for the block device. So if I say ls block, uh, these are all the different events. So for every event, there's going to be a folder. So block IO, back merge, bounce, complete, where that's when the disk request is actually completed. Queue and RQ insert. So it's basically inserts the request into the disk queue. This is when it's issued to the disk, and so on and so forth. So I'm not going to get into the details of this. And then here you have the enable. Let's say you want to, so if you put a 1 inside of this enable, all of these events are going to be enabled, right? What else do we have? We have events related to the scheduler by the name of Sketch, somewhere around here. Yeah, okay, I'm gone blind. Here, there we go. So if I do ls schedule, these are all the scheduler events, right? And we have power management events. We have actually system calls. This is system calls. Don't bother with this one. System calls. And I'm not going to actually explain every one of these, but just saying, but so for instance, just give you a few examples. Syscalls, you see that all the different system calls are here. So if, let's say, you wanted to trace all the system calls, you would just, this enable guy, you put a 1 in here, or you wanted to say only trace the accept system call. So you would only have to enable this guy. And then I'll show you how to do that. But there is like an enter for system call events. There is an enter event or an exit event. So this is when, because system call is like a function call. So whenever you enter the system call and then whenever you exit the system call, then these are separate events that are emitted by the kernel and put into a buffer for later analysis. Let's say you want to know how much time it took you to run a certain system calls. And then these are socket buffer events for the networking, and these are actually before you reach the transport layer, and this will be when you reach the transport layer. Um, these are for ARP. These are for networking. These are also for networking and API, and many events. It's actually the this is for my Wi-Fi driver, right? Yeah. So let's see now. Let's say I want to enable scheduler events, and usually scheduler event is the first thing that you want to enable because you want to know what was running on the CPU at a particular instance of time, or maybe you have like your CPU is 100% utilized, or and you want to know who's using it, or maybe you have a deadlock, or you have some process that's never being scheduled on the CPU, and you just want to know why. CPU is idle but the system is sluggish and you want to know why, right? Things like that. So let's go in the schedule folder, and well, obviously, well, the enable is going to be 0. Yeah, obviously. And let's say, well, if I do echo 1 into enable, and all of these are going to be enabled. All of them are going to be enabled. And now I'm going to go out, but that doesn't mean that I'm going to be doing any tracing. There's more, right? So for me to actually start tracing, I have to enable a global tracing flag, which is somewhere, yeah, tracing on. So right now, tracing on is supposed to be by default 0, right? Well, it's 1 actually. Okay. Well, um, anyways, I'm just gonna turn it off for now. Go 0 and to tracing on. Okay. Now it's 0. So I'm not tracing. Like once I echo 1 into this guy here, it's going to start tracing whatever trace is enabled. It's going to start tracing whatever event actually is enabled. It's going to start tracing that, which is going to be all the scheduler events. Now, once those events are intercepted, they get written into a file trace. So this file contains the trace. So if I do cat trace, for instance, it's going to show me whatever it is in the file right now, which is, you see, a lot of events. Because as you know, tracing was already on and I turned it off, right? So all those events are there, right? Let me just make this as full screen. Okay. So what I want to do always, and make sure you do this, is that you want to flush this file out. You want to empty it. So you would just echo nothing into it, right? Then see, it's empty. But well, as I said, again, this is like a pseudo file. This is a file that it's in the RAM. This part is just the legend, right? It tells you the tracer is NOP, and 0 entries in the buffer, 0 entries written. Obviously, there are 16 cores and whatnot, right? It's just empty. So this is just the legend part, which is going to always show up. But other than that, this is empty. Okay. Now I'm going to start tracing. So I'm just going to say echo 1 into tracing on, right? And I'm just going to wait a little bit, and then I'm going to say 0. Oh, stop tracing. Okay. Now let's see what we have. So I'm just going to say cat trace, and this is what we have collected. So you see all the scheduler events, schedule this, schedule that, It's all scheduler events. Now, it is the time frame is 14 thousand seconds and 14,614 seconds, point 331 milliseconds and 266 microseconds since boot. So since my system has booted, this is the time in microseconds, like in seconds dot microseconds, that has elapsed since the boot. This is the CPU core starting from 0 that this event was intercepted on, was actually triggered on. This is the actual event, and this is the event parameter. CPU, so timestamp, event, event argument. And this is, in fact, the process that was running uh, during which this event triggered. So what this is basically telling me, how do I read this? I read it as follows. When the bash process was running, or the bash thread was running, with the thread ID 32365 on core 002, on my third core, if you may, at this time after the system was booted, this event occurred, and this is the argument to the event. Now, forget about the arguments and whatnot, like why it says CPU equals 10. That's irrelevant here, right? It's got nothing to do with the core that kind of this event happened on, because I haven't explained what this event really is. But this is just how this whole thing can be read. And this idle obviously means that when this event happened, the CPU was idle. Which CPU? CPU number 2. Okay, so you get a kind of a glimpse of what the CPU was doing, right? So I have, like, 6114, and then if I go all the way up, hopefully I can reach the top. Well, unfortunately I cannot. So anyways, these are my events. And let's do another, like, I'm just gonna cat this one more time and then type it to less so I can scroll it. Yeah, there you go. So it tells me that there are this many traces in buffer and this many entries written, right? So 427632 were the entries in the buffer, and then 449354 entries were written. Entries in buffer is basically what is dumped here. So the trace buffer, which lives in RAM inside this file, and this file is actually mapped to that location in RAM, is dumped here, and it contains 427,632 intercepted and recorded events here in this buffer. However, the number of entries that were written into this buffer throughout that tracing period is 449354, which is a little bit more than that. And what this means is that this buffer, which is actually implemented as a circular buffer, is overwritten. So maybe it's roughly overwritten by like 22,000 events. So 22,000 events were overwritten because the buffer got full and it kind of overwrote itself. So like the older ones got overwritten, right? So you always have the most recent ones. That's all this says, right? That's all. Now, if you want to have all of the events, you would have to increase the buffer size, which I'm going to show you in a little bit. Now, we also have some flags, IRQs off, neat rescheduling. So here, these D here would mean disabled, meaning that interrupts were disabled when this was happening. Some events like belong to a part of the Linux code that in which the interrupts are disabled, and you just want to, like, a lot of the times, actually, when troubleshooting kind of nasty problems like lockups and things like that, some race conditions, you want to make sure that interrupts are disabled where they're supposed to be and are not disabled when they're not supposed to be. So this D means it's disabled, which should be, and in this context of trying to switch between the different threads, uh, when this is happening. Need rescheduled. Here we have one case where it's N, and that basically N. So if I do need reschedule, N meaning that, so need reschedule is essentially when in Linux the scheduler has time slices, and whenever the time slice for a certain thread finishes, and it still has CPU, like it still needs the CPU to run, but the time slice is up, so it should be preempted from the CPU and should go back in line in the run queue and wait for its turn. So when that happens, so when you have actually depleted your time slice, this there should be some sort of an indication here that means that the time slice is depleted. It's time to be scheduled out, which kind of makes sense here. Because there's a new process coming in, and the idle one is supposed to be scheduled out. Now, because this is the idle process, this doesn't really matter here, okay? Um, the other one is hard IRQ and soft IRQ, and depending on, so what it says here, it means different things. So for instance, if there's a dot here, it means that you're in normal context. You're not inside the interrupt context, whether it's a soft interrupt or hard interrupt. If it's a small s, you're inside the soft interrupt context, meaning that you're processing an interrupt and this event happened. Well, that doesn't necessarily mean it's a bad thing. It's just giving you information. If it's an H, it means you were inside a hardware interrupt, a request coming from either disk, network, or some other external device on your PCI, for instance, or keyboard or whatnot. A capital H would mean that you are inside a hard interrupt that occurred inside a software interrupt. And usually you don't have a soft interrupt occurring inside a hard interrupt, right? That doesn't happen because when you go into a hard interrupt context in Linux, you disable interrupts, right? So it's you don't get the other way around, but it's usually you could get hardware interrupt inside a software interrupt, right? So that's what it means. And then the preemption depth and whatnot. So those are kind of maybe more advanced stuff that I don't want to really get into here. And yeah, so here it tells you that, okay, actually CPU3 buffers started from here. So before that, those like CPU buffer 3 was nothing like the events, because CPUs generate events at different paces, right? Uh, because they're executing different parts of the code, right? And it's not guaranteed that the events are generated at the same pace, right? So obviously, when you look at the buffer of your trace, and there are these per CPU buffers, by the way, which are merged here into one buffer. Every CPU will start at a point in time, but they will all end at the same time, right? But the first event arriving on each of these CPUs doesn't necessarily have to be the same time. So there could be some time difference between when the buffer the buffer for each CPU starts, and that is entirely normal. Just telling you what this means, right? Yeah. So this is basically what you get, and um, if you well, you can definitely copy this file, copy this trace somewhere, and then save it, on the disk, because this is actually on the RAM, and then save it for further inspection, and whatnot, right? Just by doing normal copy. You can also go inside this folder per CPU to see per CPU buffers, right? I have 16 cores, so 16 folders. Let's go into CPU 0. This is the status for the buffer events for events in the buffer of CPU 0. And you can see that, okay, so let's say, let's just look at this cat stats. Sorry. It tells me that I have this much entries here, right? And 0 have been overrun. So I'm good, right? And it all these entries, these are the number of events, amount to 1.2 megabytes, right? And then the oldest event is that this was intercepted at this time, and the that's the oldest event. We don't have the newest event because it's actually now the newest event would be now, which is the now time. But I'm not tracing right now, right? So that doesn't tell me what is the oldest the newest event. Anyways, it tells you that when is the beginning of the buffer. So you want to know how old your buffer, how old are the events in your buffer. That's how you get an idea of that, right? And then you have 0 dropped events here, so it does that for you, right? um uh yeah, we can probably do this for a bunch of other CPUs as well. So if I say stats, give me all of it, and maybe, yeah, so there you go. See, you see overrun. So some of these CPUs have overruns, right? Well, this one has overruns. This one doesn't have an overrun. So that amount of overrun, like 20 something thousand, kind of comes from here somewhere. So some of the CPUs had some overrun, buffer overruns. Um, And this is the buffer size in kilobytes for a CPU, a particular CPU, the CPU 0. It's actually 1404 kilobytes. It's 1.4 megabytes roughly. Okay, so if you want to increase this, then just go there and say echo the size. Let's say I just want to have 32 kilobytes. Well, actually, I'm reducing the size here, but just for the sake of it, to buffer size KB and cat this, and I have 32 kilobytes only. Okay, so next time I'm going to trace, this is only going to hold 32 kilobytes equivalent of events, not 32K events. Okay, 32 kilobytes, which is going to be very small. What else do we have here? We have a trace here and a trace pipe, and a trace pipe raw. So this trace is basically the equivalent of the trace file that we had, but it's only for this core. So it's not merged, right? It's not merged. See, it's only for core 0. For whatever reason you may want to have this, so just look at per core, right? And then we have the trace pipe. If I do trace pipe, this trace pipe is basically operating in a producer consumer mode, meaning that events are written from into it, and once I read from them, the event is going to be taken out of the buffer. So it's going to free the buffer. Like that event will leave, and it will make room for more events. So if I read the trace pipe, and if I read it the second time, I'm not gonna see anything. So that's it. Cat my trace pipe, that was in it. Second time, nothing's in the trace pipe, and it kind of blocked because now it's waiting for something to be written into it so it could um, print it, right? Now, let me actually, you know what? I'm gonna open another terminal and just gonna bring this terminal here. What I'm gonna do is I'm gonna bring this by that side. Actually, better idea if I put this here, put this guy here. Okay. So now what I'm gonna do is I'm just gonna stop this. And I'm gonna go and put the right buffer size again, like 1408. I'm gonna put it in the buffer size, cat buffer size. Right, good. if I'm gonna go out and I'm gonna go one step back, and I'm gonna actually show you that this trace pipe exists here as well. So I can use this trace pipe, right? Trace pipe. So now I'm actually depleting this pipe, okay? You might wonder, why did I have something in this pipe? Well, I only emptied the pipe for CPU 0. The others are still full. Those buffers are full, right? So here I kind of emptied everything. Now, if I do this again, nothing's going to be there, okay? So what I'm going to do is, okay, and then also there is a buffer size in kilobytes here per CPU, and also the total buffer size. If I do cat buffer size, see, this is the per CPU buffer, and if I do the total, this will be the total buffer size, just 16 times that for me, right? So I can change any of these. Now, I usually tend to change this one. Now, in this case, what I'm going to do is I'm just going to, just for the heck of it, change this to 32 kilobytes and put it in buffer size. So every CPU is not going to have, actually, sorry, every single CPU will now have a buffer size of 32, which times 16 is going to be 512 kilobytes in total. Now I'm going to do the tracing again. I'm going to do echo and trace. Well, it's empty, but I'm just going to do it, to clean this up. What I'm going to do is I'm going to say, actually, I'm going to do echo. Well, you know what? I'm going to say cat trace pipe. I'm just going to look at I'm just going to look at the trace pipe. Okay. This is the trace pipe. And over here, I'm going to do sudo su, go into sys kernel debug tracing, and then I'm going to say echo 1 tracing on, because I already have all the events for the scheduler enabled. I'm going to say tracing on, and just pay attention to what's going to happen on the other screen, on the other panel. See, I have all of these events now, they've been written here, and then I'm going to say stop the tracing. Now it's stopped. Done. That's it. So like, if for whatever reason you want to have, to just look at it as it's happening, that's how you would do it. But then you're gonna lose the events, right? Now the raw, there's a trace pipe raw in not here in the per CPU folder. That is the raw events in binary, so it's not translated into this text form. You didn't really need to use that much, so I've never actually used it myself, but just to know that there's something like that there. Now, let's say, okay, I don't want to generate all of these events. These are just too much. Like if I go and if I go in my scheduler, actually cd events, scheduler. There are so many events. I don't want all of them, right? Usually you'll need a subset. So what I'm going to do is I'm going to echo 0 into enable. I'm just going to disable them all. Now, what I'm also going to do is I'm going to enable them as I want. Usually, sketch switch is enough because it tells you what context switch happened from what process to what process. This is usually the bare minimum that you would need. Sometimes you would need the wake up and the waking to understand who's basically unblocking who. All right, but not all the times. So in this case, I just want to enable this. So what I'm going to do, actually, let's do an ls here, sketch switch. You can see that there's an enable here. There's a filter as well here. We haven't used that yet. And then usually these three are the ones that I use most. So if I write 1 here, echo 1 into schedule switch enable. Okay, this guy is enabled. Now, I could have done it from here, but then like I'm going to say cat trace pipe. Oh, not here. Sorry. Here. Cat trace pipe. I just want to look at it online. Okay. And I'm going to say echo 1 into tracing on. And these are only scheduler events. Stop tracing so you can see that. Yeah, let me just blow this up. It's all sketch switch, sketch switch, sketch switch. That's it, right? That's all. Telling what was the previous process and what's the next process, which is in this case swapper. It means idle is the idle process on core number 2, and so on and so forth. So actually you can see, yeah, it was here, pulse audio, and then next time CPU2 has something, it's as an event, it's already in the idle. It's like happening in the idle process, which means that the sketch switch, because of the sketch switch here, that we went from pulse audio to swapper 2. So you can actually understand what's happening, which process is context switching into which process, and yeah, you get that. Sometimes what you want to know is you want to know like the different fields of an event, the format of an event, if you may, or a trace point. I'm going to show you how to do that. Let's say I'm interested to know what's the format of the information for the scheduler event. Sketch switch. Here, if I do cat format, it's going to tell me that, yeah, okay. So look at this part. This is the important part. So there are two segments to it. The first part, just ignore this, right? These are the arguments. Prevcom, look at here. Let me just blow this up a little bit, maybe, or just reduce the size. That's too much. So if you pay attention, you can see that there is, okay, this event, right? This event, sketch switch, prevcom. You see this? Prevcom? Okay, this is here, this guy, prevcom, which is a char 16 at offset 8 and size, so 8 bytes into the event, kind of. You probably don't care about the offset, but you care about the size. It tells you that it's going to hold a string of size 16, which is null terminated, so it's 15 actually. And then previous PID, previous priority, previous state, next command or process name, next PID, next priority. That's all. And then it's going to tell you here the actually print format. It's going to say prevcom equals %s, which is a string, prev PID, prev this, and then like equal greater than, like an arrow here, and so on and so forth. And then these are the parameters. So this is actually taken from this is part of the kernel code, by the way, right? And if you look here, it's the same thing. See, prevcom equals the string, this guy equals an integer, and then here, and then the arrow, and so on and so forth. So here you can understand what the format of an event is and how different fields should be interpreted. Okay. Now you can also go to the kernel code and search for this, and I've done this in many of my videos to actually find out, like go to the actual code in the kernel to find out how this trace point is called and what are the different fields. But it's pretty much the same thing. You're gonna find pretty much the same thing over there as well. I'm not going to talk about the filter right now. That's a little bit probably more advanced. I'll leave it to a different video. But yeah, that's about it. I guess I kind of covered whatever I wanted to cover for the first video here. In the next video, I'll be talking about trying to narrow down these events more by using different kinds of filtering mechanisms, right? Filtering for a certain process, filtering for a certain field being greater than a certain value or less than a certain value, and things like that. So, hope you enjoyed this. Please stay tuned for newer videos coming up about tracing.